If you've used a product like REW, Room Equalization Wizard, or have ever put a microphone into an untreated listening room, you will get the shock of your life, because here's our friendly dB versus frequency chart. What you will find is that the manufacturer's specification for his loudspeaker is something nice and flat like that, let's say, but by the time you put it into the ordinary untreated room, it actually looks like something like that. And if you want to do something about that, you're either going to have to apply damping to the acoustics of the room, which may or may not be domestically acceptable, or you might be lucky and be able to introduce some sort of electronic counter peaking system, such as mini DSP, which in effect will take these peaks, apply electrically the opposite effect in the loudspeaker, the peak cancels the trough, and you get a flat response. Of course, you move your head a metre or so either way, you've got a somewhat different picture of resonances in the room, so it won't cancel those. So the best solution is always a mechanical solution, in other words, treatment of the surfaces. So there are two sorts of resonances that we can experience in the world of electronics or acoustics or mechanics. And one of them is called a high Q resonance, which looks something like that. High Q, which has a center frequency, an amplitude, so many dBs, and a width, which is defined on the shoulders of this peak in delta, so it is as so many hertz, a bandwidth, as it's called, bandwidth. You can synthesize that with a Coke bottle. Tip out some of the contents, blow across it, and you will get a good strong resonance. But you've probably noticed that it takes a second or two of huff to get the thing up to pitch. But once it's at pitch, you can remove the stimulus, your breath, and it will hold that. And we need this intensity of resonance for creating musical instruments, because we need them to hold their pitch during the whole performance. We need them to have a defined pitch, and to hold that pitch, and to do that we need a high Q resonator. Conversely, a low Q resonance could look something like that. I haven't drawn it symmetrically, but it doesn't make any difference. Its center frequency is, in this case, it's about here. Should have lined them up really. It has generally much lower gain, but the important thing is that the amount of energy underneath the curve for the low Q resonance is a lot more than for the high Q one. Not especially as I've drawn it, but that is the reality. What does that mean? Simple. It means that if this frequency response here was the keys of the piano from the lowest right the way up to the highest, and we had these two different resonance systems in this piano, we would have to play up the piano to hit this one, and all the other notes would sound dull until we got to that particular one, and off it went. But in the case of a low Q resonance, it really hardly matters where we play, although it is a bit concentrated in the middle. Anywhere in the middle here is going to excite this resonance and is going to colour the tone that we hear. Doesn't make a good musical instrument to have a broadband resonator. We need a sharp resonator to be able to tune it and get it to hold tune. So that's the background. How does this relate to audibility and loudspeakers and rooms and electronics and so on? Well, bit of counterintuitiveness here, methinks. I remember when I first discovered this, I was quite disbelieving of it really. It was discovered in the 1970s. No, it probably wasn't, probably before then, but this was the talk of the 1970s. For example, loudspeaker coloration Barlow and Fryer and Stevens did a lot of, and Harwood, of course, did a lot of work on this. And they found that if this was the frequency response of the audio system, if I asked you to draw a high Q or a low Q resonance on this graph as superimposed on top of the audio, what would be more objectionable? What would be more obvious? Would it be the low Q or the high Q? And I bet everybody, including me, I hasten to add, would probably say, well, of course the high Q resonance would be more obvious. It's got a defined pitch, it's loud and air. Actually, the opposite is true. Under general conditions. That is to say, it was found that with music, jazz vocals, for example, the high Q resonances had to be above the bass line, which is here. They had to be above, they had to be louder than the bass line by so many dBs before they were audible. Surprise? Maybe not, if you've seen TechTalk 1 and 2. On jazz vocals, they could be, they on white noise, they would have to be below the bass line by so many dBs, on white noise to be inaudible. But in the case of a low Q resonance, to be inaudible, they always had to be well buried below our baseline audio by quite a few dBs. Otherwise they were clearly audible. Okay, so how does that relate to tone adjustment in hi-fi systems? Well, it means this. Back to our friend, if this is our system frequency response, and we were lucky enough to have a bass or treble or tilt control, these controls are low Q resonators. And a small adjustment, maybe only a decibel or so, of these controls, which has the effect, in the case of the bass, of, say, shelving it up like that, or down. And in the case of the treble, similarly at the top end, or the tilt control does them both together. A small variation in this control, maybe only a dB or so, has a massive effect on the audibility of the system, because the ear is very sensitive to low Q resonances at the baseline in normal program material. And this also means that if a loudspeaker, for example, had a frequency response, or let's say there were two loudspeakers, and let's say this is A. If loudspeaker A had a response that looked like that, loudspeaker B had a response that looks like, for example, that even small difference, maybe a decibel or so, would be highly distinctive compared to the flat loudspeaker. And again, you have to be very careful when you're doing an A-B comparison, because that would be audible, whereas a series of peaks, even quite pronounced ones, very narrow peaky ones, might well be completely inaudible, because the statistical chance of those resonances being stimulated by notes in the music is much lower, because they're so narrow and there's so few notes in that range that with everything else playing they will most likely be disguised. This effect, by the way, varied between white noise as a stimulus, classical music as a stimulus, and jazz vocals, but it's something else to be aware of. Hope you enjoyed that.